Hello students, today we're going to talk about water. So in the previous presentations we have been talking about the macronutrients. We started with carbohydrates, then with lipids, and finally proteins. But there's a component that is so important that we have to consider it, and that component is water. So today's objectives are to explain the water usage in the US for food crops, to identify the components of water, a water filter, to describe the three physical forms of food, to describe common beverage types, to recognize the influence of water in food, to distinguish between moisture and water activity, and to define low moisture foods. So if we think about what's the state has the most irrigated land. So we know that for agricultural crops, water is very, very important. And if we think about agricultural crops and the use of water and irrigation being a very modern and efficient alternative, we have to think about where this water comes, the use of water, how we recycle water, and the cycle of water. If we take a closer look at this map, we can see where the irrigated areas in the US are. We can see here we have California, the Midwest, here southern parts, Florida. Here we have also a concentration of irrigated land, and also here in the northwest and here. And these are the parts of the US, the regions where most agricultural crops are produced. This is a chart from 2017, and it tells us that Nebraska was the most irrigating agricultural land, and California was the second one. If we take a look, and you can do that as doing a search in the internet, California has in 2023, 2024 gone to the first place. So now California is in terms of percentage, the largest irrigated state in the US. And also this is what we talked about in the previous slide. We have then Arkansas and Texas, Idaho, Colorado, Kansas, and we have here Florida and Georgia, which are the concentration of irrigated land that we saw in the previous map. So fresh water is produced or is needed to produce all these type of food. If we see fresh vegetables, we need around 20% of fresh water to produce vegetables. So agricultural production requires a lot of water, and also manufacturing of food products requires water, mainly beverages. And we can say that around 1/3 of the nation, fresh water is used for the production of food and beverages. And in this chart we have what percentage of water is required to produce all these types of product. So water is a resource that is so important, and there is a lot of treatments, both pre-treatments, so before we use water, for example, for drinking, for processes, and we also have post-treatments, which is the treatments of what we call wastewater, or that can come from processes, manufacturing processes, from houses, restaurants, hotels, etc. So why do we use filters? So filters are used for different purposes. So here we have an example of a filter that we use at home, and we have a mesh screen here that will remove larger particles. We don't expect to have larger particles in our potable water, but this is just as a prevention. Then we have activated carbon. And activated carbon is mainly to remove flavor flavor compounds that we may not like. Also helps with removal of chlorine, and then we have an ion exchange resin, which is a more so this is like a bigger pore, this one, then the activated carbon, and then the ion exchange, which is like a smaller pore, and that is used to remove ions, for example, that we may not like, and that are associated with hardness. So maybe some sort of like sodium or chlorine or calcium. So this can be removed. And these are the components of the filters. So activated charcoal helps with color and flavor and other. Ion exchange mainly for ions removal, and particle filters, which is the coarse pore size, which will help with like larger particles removal. So this is just a nutshell of water filtration at home, but in the industry there's many different types of filters and technology that is used to have the input of water that is required for manufacturing. Sometimes there's a ion balance that is required depending on a type, for example, of beverage that we're going to make. So there's a type of quality of water that we need, and that's how we use, or why we use, this type of filters. So I would recommend you guys to watch activated charcoal and how it works. So activated charcoal is widely used as a filtration aid in water filters, mainly the ones used at home, but also in the industry. And as I mentioned before, it helps with color removal, flavor and taste removal. And I recommend that you guys watch this video. So we know that water can be present in three phases. So water can be present in the solid form. We know it as everybody knows, ice. Then it can be present in a liquid form, which is the form that we drink, and in the gas form, which will be vapor. And if we translate these to food, we can also find food in like solid, liquid, and gas phases. So if we think about solids, we mainly think about raw materials that will need hydration, for example. So some solid foods, maybe some flours. Here we have a picture of coffee beans, nuts. So those are mainly solid foods. But even when we have solid foods and the appearance is solid, all food contains an amount of water. Even when it's a small percentage, like say 10%, it always contains water. So the second form will be liquid, and this is the only physical form that we consume as it is. And there's like, let's say in beverages are the main example of liquid foods, but we also have, for example, oils as examples. And then we have gas, and then we add gas to liquids or solids, depending on what we want. And most of the gas that we add in food manufacturing is air or CO2, carbon dioxide, and carbon dioxide is a byproduct of this metabolism. And this has to do a lot with baking, leavening in baking, and also carbonation in beverages like sodas. So some stable combinations. So a solid plus a gas. When we want to make a foam, we whisk gas into a liquid or a solid. For example, a liquid, let's say egg whites. So if we whisk gas into air into egg whites, and we continue whisking, there is an interaction of this gas with proteins that are present in egg whites, and then we form like a meringue. And then that can also, if we bake them, then we will get this type of solids, right? So this type of meringues. We can also whisk gas into a liquid or a semi-liquid mixture, and then that can be converted into a solid. And one example will be marshmallows. Another example, which is not a foam, but it's not just a foam, but it's the incorporation of air into a liquid mixture. It's and then as air is incorporated and temperature is decreased, we form ice cream, which is also very well known by us. Then we have a sponge that is obtained by incorporating gas and by the action of mixing or kneading. The other combination that we have is liquid-liquid. So the most typical example of a liquid-liquid is what we call an emulsion. So adding oil slowly while beating vigorously, like for example in mayonnaise, salad dressings, margarine. So these are emulsions, and these are liquid emulsions. Well, mainly in the case of salad dressings, and where margarine becomes more a solid, but it's also an emulsion. So this is another example that I would like you guys to watch, is like what's the science between meringue making, and we talk a little bit about proteins, the incorporation of air, and how this changes the configuration and leads to the formation of a solid, and then when it's baked, what happens. So I recommend that you guys watch this video. Then we have a combination of liquid plus gas, and this is a combination that is not very stable. So this is not stable, and this is called carbonation, and it needs pressure to contain gas. So if we think about a can of Coke, for example, when we open it and we dispense the Coke like in a glass, we can see bubbles. We can see that there's bubbles, and these bubbles are carbon dioxide that have been partly solubilized in the liquid. And then we see that the bubbles go to the top, and some of them will reach the top and then go to the headspace. And so this liquid gas is not a very stable combination. Like if we leave that, say, glass of Coke for a while, then eventually we will lose all the carbon dioxide. So to contain the carbon dioxide, and in this liquid, in this soda, we need we need pressure. So that's why we have our cans or beverages normally in cans, glass, sometimes plastic, but they are under pressure. When we open them, that pressure is released, and then we eventually will lose that combination of liquid and gas. This is an example of a video of how carbonation works, how bubbles are formed, distributed, and I also recommend that you guys watch this video. So if we think about a carbonation and beverages, so carbonated beverages are just one type of beverages. We can divide beverages here in like 3 different categories. So the first one is beverages that are formed by extraction processes, and 2 examples are coffee and tea. And an extraction process requires a solid and a liquid, and normally the liquid is water, and it's at a high temperature. Depending on the temperature that we want to use, we have a ratio of solid, which is coffee or tea, and then by the action of mixing or pressurized water and temperature, we have an extraction process. So we extract the compounds that are present in coffee or tea, and then those compounds migrate from the coffee and tea to the liquid, so to the water, and then we get the beverage. So these beverages that we like a lot, like coffee and tea. Then the second type of beverages are carbonated beverages, and then this type of beverages, we can use carbon dioxide, and and inject that into different types of beverages, for example, sodas, sparkling water, and then we can also have a natural carbonation or process, which it's done through fermentation. So when we use fermentation, and we're going to talk about fermentation in the third week, we can also, yeasts can produce carbon dioxide in their metabolism. And while converting sugar to alcohol, they also produce carbon dioxide. And this happens in fermented beverages, for example, like beer or kombucha. And this is a natural fermentation process, and it produces carbon dioxide. And the other is carbon dioxide that we inject into the different beverages. And then we can talk about alcoholic beverages, and we can define them into two main categories. So the first one are fermented beverages, and the second is distilled beverages. So fermented beverages, the main examples are beer and wine. So it's very important that you guys remember that these are fermented beverages. And most recently, like kombucha has become very popular, and this is another fermented beverages. There's other fermented beverages around the world, typical from different parts, different cultures. And if we think about the percentage of alcohol, so kombucha is very low. Like traditional kombucha is less than 0.5%. We can have other alternatives that are higher in alcohol. And beers around 5 to, say, the high percentages, 8%, 9%. And then our wines will be around 12 to 15%, but this can vary depending on like many things, varieties, and so. So when we take these fermented beverages and we concentrate them more by a process that is called distillation. So in this process, we want to separate alcohol from water. And by this distillation process, we also separate flavor or aroma compounds, and that's how we make the distilled beverages. So all distilled beverages first come from a fermentation process, and then they go through a distillation process, which is a concentration process, in which we will have the final product will have high alcohol percentages, say around 35 to 45%. And then in this category, distilled beverages, we will find all like tequila, mezcal, vodka, whiskey, and all these different types of distilled beverages which have a higher alcohol concentration. And of course, some of them are clear, then others are aged, and they have a different color because of they are aged in like wood barrels, and this gives them a distinctive color. So when we think about extraction, the best example will be coffee. Coffee, we normally think it's very acidic, but it's not that acidic. So normally a coffee will have a pH of 4.5 to 6, and compared to our stomach pH, which is between 1.5 and 3.5. And pH is a measurement of how acidic or basic a food or substance is. And if you guys recall, pH goes from a scale of 0 to a scale of 14, in which we have 7, which is our neutral pH, and in anything below 7 will be in the acidic side, above 7 will be like in the basic side. But most foods are lower than 7. Normally water is around like 6-8, pH of 6-8 to 7, but most of foods are lower, and depending on the foods that we're talking about. But pH is very, very important in food. So how can caffeine be removed? So a lot of consumers want decaffeinated coffee or tea or other types of beverages. So caffeine is a compound that is soluble in water, and it can be removed by three main methods. The first one is with a solvent. So caffeine can be extracted with a solvent that is then evaporated. The second method is we can remove it with carbon dioxide extraction. And the third one is remove it with water extraction and then different types of filters. So removing caffeine or producing decaffeinated coffee is an intensive process, and it requires a lot of technology. So how can we call a coffee decaf coffee? So yes, we can call a coffee decaffeinated if it has less than 2.5% of the original caffeine, and that's how we can call it decaffeinated. So they have to meet these type of regulations, because the process of extracting or removing caffeine is not 100% efficient. But in order for a coffee to be called decaffeinated, it has to meet these regulations. So water how is it used in food? It is almost everywhere and in almost everything. So water is very, very widely used. As I mentioned before, water is part of all food, regardless, you name it, and it will have a percentage of water. If we think, for example, about fruits and vegetables, so water makes up around 85% or more, in some cases 90% or more than 90% of the composition. And in other components, like dried products, it will be like 10% or less. So that depends on the type of food, the type of product. And food processing relies a lot on water, and not just as a raw material for processing, but also many of food processing or preservation techniques are based on water removal, lowering the water content or the water availability. And we're going to talk about food processing during week 4. But water is so important in the food that we consume, and in general for our health. This is a video about, I think you guys already watched this video, is sourdough bread, and the main idea here is how water is incorporated into like baking, so bakery products, and then how this mixture of flour and water and yeast, in the case of sourdough, or yeast and bacteria, will form carbon dioxide, and these will, as we mentioned before, create this 3D mesh where the gas is trapped, and these will give this texture to bread. And this is just an example of how water is used in processing. The other example that I want you guys to watch this video is ice cream. So ice cream is made from milk, and more than 88% of milk is water. And how water in milk is transformed during ice cream making, as we incorporate air and we lower the temperature, we are going to go from a mixture or an ice cream mix that is liquid into like a solid, which is ice cream. So how this works, and there's a lot of science and technology in ice cream making, so I also recommend that you watch this video. So as I mentioned before, all food has water and moisture. We could say that we can find it in two ways. So one of them would be bound to molecules, so bound to molecules like sugar or proteins, carbohydrates, and the other is free. So we will call this free water, available water. So we're going to define two terms that are very important. The first one is moisture. So moisture is water content, and we can use the term moisture. So sometimes we'll say, oh, well, what's the water content? Like I mentioned before, let's say, what's the water content of apple? Okay, the water content of apple, let's say, is around 90%. what's the water content of apple chips? So apple that has been dehydrated, well, maybe the what moisture content of apple chips is around 12% or maybe less. And this moisture content is available for all the foods that we eat, and we can also calculate it in our assignment tool, in which we're going to analyze the composition and nutrition facts. We're going to calculate water. The second term is water activity, and water activity symbol is like AW, and that we can say it's the available water. So water activity goes from a value of 0 to a value of 1. So if we have 100% water available, then that will give us a value of 1. So many food products have high values of water activity, let's say around 0.95, and we're going to talk about how this affects the food stability, shelf life. So water content is very tightly related with this. So we use these two different terms to describe water. Moisture content, we use it to determine yielding processing. As I mentioned before, some processes will require water removal, like concentration or dehydration, and that this will determine the yield of the process. We use also moisture to determine the texture. So this will depend on the amount of moisture content will give us the end point of processing. For example, in bread or cake, it has to achieve a specific moisture content. And then water activity, that will determine the safety and quality of food. So if we have high water activity, as I mentioned before, like 0.95 or more, then this will make our foods less, the shelf life will be shorter. And we have low water activity, then the shelf life will be longer. And this is in terms of processing and preservation. We sometimes play a lot with water activity and the incorporation, for example, of solids like sugar, like in jam or jelly making. We have a picture of raisins. So these are examples of how by the addition of solids, we can lower the water activity and thus help shelf life be longer than the initial. So what does FDA say about water activity? So if we have a food that has a water activity above 0.95, that would indicate that we have an environment that is that will support the growth of bacteria, yeast, and mold, and these are microorganisms, and these microorganisms will deteriorate the food, and that does make the shelf life very short. If we can lower this water activity and have it controlled to 0.85 or less, that will give us a product that will have or inhibit the growth of microorganisms, and so will allow us to have a longer shelf life. So the shelf life is the time that the product is safe for consumption, and sometimes we as consumers can see that by the expiration date or the best by date, and these are terms that we are going to talk about later. So low moisture foods are foods that are naturally low in moisture, or that have a high, if they are high in moisture, they have been subjected to drying or dehydration, and thus most of the water has been removed. And some examples of low moisture foods are dried fruits and vegetables, cereals, grain, nuts, seeds, and dried herbs. And these low moisture foods have a long shelf life, and the water activity has to be lower than 0.85. So if you have any questions, please reach out to me. And with this, we are concluding our water presentation.